Section 9.4, Covalent Bonding and Orbital Overlap. The VS-EPR model provides a simple means for predicting the shapes of molecules. However, it does not explain why bonds exist between atoms. In developing theories of covalent bonding, chemists have approached the problem from another direction using quantum mechanics. How can we use atomic orbitals to explain bonding and to account for the geometries of the molecules? The marriage of Lewis's notion of electron pair bonds and the idea of atomic orbitals leads to a model of chemical bonding called valence bond theory. By extending this approach to include the ways in which atomic orbitals can mix with one another, we obtain a picture that corresponds nicely to the VS-EPR model. In the Lewis theory, covalent bonding occurs when atoms share electrons, which concentrates electron density between the nuclei. In the valence bond theory, we visualize the buildup of electron density between two nuclei as occurrence when a valence atomic orbital of one atom shares space or overlaps with that of another atom. The overlap of orbitals allow two electrons of opposite spins to share the common space between the nuclei, forming a covalent bond. The coming together of two hydrogen atoms to form hydrogen is depicted in figure 914. Each atom has a single electron in the 1s orbital. As the orbitals overlap, electron density is concentrated between the nuclei. Because the electrons in the overlap region are simultaneously attracted to both nuclei, they hold the atoms together, forming a covalent bond. The idea of orbital overlap producing a covalent bond applies equally well to other molecules. In hydrochloric acid, for example, chlorine has the electron configuration of neon 3s2 3p5. All the valence orbitals of chlorine are full except for one 3p orbital which contains a single electron. This electron pairs with the single electron of the hydrogen to form a covalent bond. Figure 914 shows the overlap of the 3p orbital of chlorine with the 1s orbital of hydrogen. Likewise, we can explain the covalent bond in the chlorine molecule in terms of the overlap of the 3p orbital of the one atom with the 3p orbital of the other atom, as shown in figure 914c. Figure 914, the overlap of orbitals to form covalent bonds. A. The bond in hydrogen results from the overlap of the two s orbitals to form two hydrogen atoms. B. The bond of hydrochloric acid results from the overlap of a 1s orbital for hydrogen and one of the lobes of a 3p orbital from chlorine. And C. The bond in chlorine results from the overlap of the two 3p orbitals from the two chloride atoms. There is always an optimum distance between two bonded nuclei in any covalent bond. Figure 915 shows how the potential energy of the system changes as the two hydrogen atoms come together to form a hydrogen molecule. At infinite distance, the atoms do not feel each other, and so the energy approaches zero. As the distance between the atoms decreases, the overlap between their 1s orbitals increases. Because of the resultant increase in electron density between the nuclei, the potential energy of the system decreases. That is, the strength of the bond increases as shown in the decrease of energy of the curve. However, the curve also shows that the atoms come very close together, the energy increases sharply. This increase, which becomes significant at shorter internuclear distances, is due mainly to the electrostatic repulsion between the nuclei. The nuclear distance, or bond length, is the distance that corresponds to the minimum of the potential energy curve. The potential energy is the minimum corresponds to the bond length. Thus, the observed bond length is the distance at which the attractive forces between unlike charges is balanced by the repulsive forces between like charges. Figure 915, formation of hydrogen. Plot of the change in potential energy as the two hydrogen atoms come together to form hydrogen molecule. The minimum in the energy at 0.74 angstroms represents the equilibrium bond distance. This energy is at that point of negative 436 kilojoules per mole, corresponds to the energy change for the formation of the hydrogen-hydrogen bond.